Hi friends, Ben again. This is a video for the differential equations class. We are looking at solving the wave equation. So previously we looked at a heat diffusion equation, and it had this nice property that we could use a technique that we refer to as separation of variables. You were looking at the equation, in that case, u sub xx equals u sub t. There's an alpha squared at the beginning, I think. But you took a look at that and you made this guess that it could be separated into a function that was only a function of x and a function that was only a function of t. And then by clever manipulation there, you've turned it into just two ordinary differential equations, both of which were pretty easy to solve. So with the wave equation, we're applying the exact same technique. It's just that we've got different differential equation. So these wave equations are meant to describe something like a wave, imagine that is propagating through an elastic string. So you have some sort of a string with the two ends clamped, and it starts out in some wave form, like maybe that. And then because it has elastic properties, the force on it is then described by that differential equation. A squared u sub xx is equal to u sub tt. So it kind of suggests, because it looks a lot the same, that maybe we're going to go ahead and try that separation of variables technique as well. But now, because you've got a second derivative on the t as well as a second derivative on the x, that means that the t functions are going to be sines and cosines. However, because of that fixed endpoints stuff, we still are going to be talking about sines for the initial position. Okay. All right. Let's see if the iPad will work, and we'll try to see some of this worked out. Okay. Here goes. And it did. This morning, it refused to work, and I have not done anything to it since. So, yay. All right, so the wave equation, partial differential equation, what we're looking at here, we're describing the motion of an elastic string with fixed ends. So from physical properties, we get this equation of a squared u sub xx equals u sub tt. Now the a squared is going to turn out to be determined by the string. I forget exactly what it is. I think that the tension on the string, as well as the density of the string, is going to determine certain things about it, but it's going to be constant for a certain string. So either we're going to have the initial position given by u of x0 being f of x, or we're going to have the initial velocity be given with the assumption that the initial position is 0. So if you've got the initial position, then your solution is going to take the form of a summation of sines times cosines, right? If, on the other hand, you've got your initial velocity given, then you're going to have a summation of sines times sines. So because of the fixed endpoints, you're going to be using sines for the x part in either one of these, but depending on whether you've got an initial condition or an initial velocity, that will determine whether you end up with the sine or the cosine on the second part, the t portion. Okay, so if, well, in either case, you know that you're going to do something that is along the lines of the Fourier coefficients for the f of x. So you're going to multiply that by the sine of n pi x over L, integrate from 0 to L, and then take this 2 over L because you're essentially taking an average. Okay. And if you are instead doing this for an initial velocity, then you'll take the initial velocity g of x, multiply that by the sine, integrate, but now the thing that you're dividing by ends up not having the L in it. And the thing that's going on with that is that when you're taking when you're talking about the sine and cosines derivatives and such with what we're working through, we end up canceling out the L in certain of the integration we do. So in any case, we've got one of these two forms, and we're just going to look at an example of working through one of them, right? Now, for a change, I got smart, and I grabbed from a textbook just a copy of a problem. So here we're going to have the vibrating string. The length is going to be 30, okay? And our equation is going to be 4 u sub xx equals u sub tt. If you have no information telling you what that a squared is, go ahead and assume it's 1 and write that down somewhere that you've made that assumption, okay? But for what we were doing here, we were given this. We know the length of the string. We know we're interested in what happens as t goes to, or as t is larger than 0. So the ends of the string are fixed. That we have to be doing that. We can look at other possibilities other than that, but that is what we're doing here to get a feel for it. And the string is set in motion with no initial velocity, and we're given an initial position. That tells us we've got the f of x for position, not velocity. And that means that we're going to be doing c sub n, not k sub n, right? So thinking about this function here, as soon as you see that format, you probably immediately think that it's going to be that temp map sort of thing that we've seen before, and it almost is. It's going to be something that has a much higher peak at the beginning and then goes down more slowly afterward, right? So we know the form our answer takes, and we just have to figure out that c sub n for it. And then we're going to have the sine and the cosine. So for that c sub n, we have 2 over L, and then the integral of the function across the interval. Since the function breaks into 2 pieces, we're going to break the integral into 2 pieces. The first part of the interval from 0 to 10, it's x over 10. The second part of the interval from 30 minus x over 20, I'm sorry, from 10 to 30 is 30 minus x over 20. So it has half as much slope, okay? All right, so then you've got to integrate those, and I am not a masochist. So instead of integrating them myself, I jump over here to Symbolab. Nope, that's not Symbolab. All right, I opened the wrong window. So my screen share here, I'll show y'all. So I just went in and said to it, I want to integrate 0 to 10, x over 10, sine of n pi x over 30. If you need to know how to get that pi symbol there, if you type \pi and then put a space, it will know that you want to talk about pi. It knows sigma and rho and a bunch of other constants as well. Once you've got it, you hit go, let it do the integration for you. And the integral turns out to be pretty messy, right? So there's that. Then for the second part of it, I hope I can show that without having to reload because I can't see what it is you're seeing. So the second integral there also gets something that is pretty messy. All right. So once we've got those two things, we are going to go right back to where we were at and just copy them down. Mirroring, press the button, it worked. Yay. Okay. And so we get this horribly messy looking thing and this other horribly messy looking thing, and we hit it lucky, and at least two pieces canceled out there. And the other two pieces, they don't cancel, but they look a lot alike. So we're going to end up with 90 and 45 is 135. And we'll put 135 over 15, and that turns out to be 9. And then we'll pull the n squared pi squared out to the front. And since it's got a factor of n pi over 3, then we can just follow it back up here, plug that back into our summation. Now we have to do 9 sine of n pi over 3 divided by that n squared pi squared. And then it's n pi x over 30 in sine, and it's n pi t over 15 in cosine. Okay. So it would be nice if we could see a picture of that. So I went ahead and found some code for how to get one of those pictures. And there we go. All right. So the code that I found, I'm trying to be good and give citations where they're appropriate, but I just Googled animate wave equation Colab Python, because I would have just said animate wave equation Python, but sometimes Colab doesn't want to play well. And because I don't want y'all to have to do your own installation of Python, I went ahead and looked for stuff that was going to work in Colab. So this guy who posted something, his name is, somebody should maybe tell me how to pronounce it, Navjot, I'm guessing, Singh. And then he gave credit to somebody named Louis Tiao. So let's take a quick look at the code that I found, and we'll see how we need to change it, right? So the first thing here is that we're taking the package NumPy, and we're going to use that, and that's come up before. Matplotlib is this package that does a lot of plotting stuff, and it works a lot like MATLAB does. And in particular, we're using the PyPlot out of that. So then we also out of that need the animation package and something called RC, radio control. I don't know, but it shows up later in this. And then this ipython.display, we're importing the HTML. So I guess the thing it's doing with the animation is making a little bitty web page and putting the animation on that, because it ends up using some JavaScript. Okay. So this first bit here generates two variables we need to reference occasionally, figure and axis. And that thing of plot.close, I guess, goes ahead and tells it that if there were any plot objects in action, that it wants to get those turned off. So then this is an important piece here if you're going to do any sort of animation, right? We want to set the X limit and the Y limit to be to some certain values, and we want to make sure that that is maintained throughout. If you do not tell it your X limit and your Y limit, every time it makes a picture, it will change the size of them because it's trying to make it fit just right. Then we have something here that I'm not entirely sure about the format of it. It has line, comma, okay? And then the setup here of ax.plot is going to plot, whatever comes next. but the fact that we give it empty brackets says that it's plotting an empty list. So it's just going to make an empty thing there of a plot. So apparently this is just some initialization stuff. And then we're going to come along here and we're going to define a function. And the function is going to do that same sort of thing over and over again. So then we define the actual animation portion of it. So the actual animation portion of it in each step goes ahead and defines a new X array. You don't need that. You could have put the X array outside, and that's what I did when I tried to modify it. And then it says for the Y values that we're going to have different Y values each time. And we're going to be doing a sine, and it's got an n times pi, and then it's got X minus 1/100th of I. Since the I we'll see later is going to end up being an integer, and it's going to end up going from 1 to 100. Kind of makes some sense. But then once it's got the X and Y, it's going to take line, which we'd seen elsewhere, and set the data for it to be the X and the Y we've got, and then it's going to return that. So that's the animation function. And if you notice here, we've got nm, okay, equals animation function animation. We're going to be dealing with the figure every time. We're going to be using the function that we named animate, and initial function equals init. Yeah, I don't really know what that means, so I have to just kind of use it, you know, just trust that it's right. This part here of saying frames equals 100 and interval equals 100 are going to have to do with how the plot actually works. You want to have 100 frames in it. And I don't know what blit means. So anyway, this part below is doing something in JavaScript about an HTML, okay? So this stuff here is a mystery to me because I do not do JavaScript. And once I hit the button, it has to think about it for a second, but once it's got it, it will have a plot for you. At which point you say, yay, wow, signs, I've never seen a sign before. But then when you turn it on, it will give the animation for it. And so all it's doing is slightly moving the sine wave at each step, but it gives that sort of sensation of movement. So for what we're doing, we have something slightly different. And so coming down through here, I've added in a part where you give it the length of your interval and then the period that you want. Figuring out the period, you should know how to do that. You take 2 pi and divide it by the coefficient of t, okay? But I called those cap L and cap T because they were going to be limits that were going to come up. And then I came along here and said capital N equals 50, and we use 50 terms. You should experiment with 10 terms or 5 terms or something and see why we want 50 terms, okay? If you don't need 50 terms, don't use 50 terms. But it turns out we kind of do. So once we had this thing going here of the length, we know that the X values, we want them to go 0 to L, whatever that L happens to be. But because we separated it off here in this earlier part, now we can come back and just change it when we want. So anyway, that's setting up the size the same as we did before. I went ahead and left it as -2 to 2 because I took a look at the range of values we're talking about. The largest X values get up to +1, and the lowest get down to -1. Not in the initial drawing, but you'll see. Okay, But then I was able to reuse like a lot of this whole initialization thing. Their init function down here, and we have to rewrite their animate function, but it's not a super big deal. I did go ahead and define a function here to give me the coefficients of my the C sub n's that we needed to figure out. So I just called it coef for coefficient, and I told it that it was going to get the variable n, and then just take 9 times sine of n pi over 3, divide it by n squared pi squared, and just return it. Okay, so super trivial little function there, but anyway. So then the t and the x down here, I went ahead and said, let's let our little t go from 0 to big T in 100 steps, and our x go from 0 to L with 100 steps. Okay. If you're looking at it and you think it kind of looks too sharp and jagged, crank it up a little bit. If everything is going too slow, maybe make those numbers a little bit smaller. Okay. But I'm just noting right here in the animate stuff, I did something that was just an initial go round before I knew how everything worked. And I have this XX thing in there that is totally not necessary. So consequently, I'm going to just come back through here, and if there was an XX, I would have to take it out, but now it should be gone. I think that's got me. Okay. So if you look at what's going on in here, this portion of it here is going to define the Y values for your graph. And it's a lot like what we saw before. We are going to start out with zeros. I keep getting these pop-ups every time I hover over something. Okay. But you get the zeros, and then you're going to just do a loop. Like in this case, I had it go from 1 to n plus 1. And it's going to just say, I'm going to add on there the coefficient of the k, and then the sine of k pi x over L, and then the cosine of 2k pi t over capital T. Now here you will notice I have used T of I. And when we step through with the animation, it's going ahead and just getting these values for I, and it just walks its way down the T's. So if you remember, the T up here was this lens space that went from 0 to T, and it just had 100 steps. And so I'm just going to take and walk through that. And so consequently, I am kind of taking a cross section or a picture with a certain time value of what the string looks like. And then I, once I've added up, 50 terms here or something, then that's going to be good enough for my Y's. And then I have to tell this that we need to set the data like that, and then it returns it because it's all going to be down here in this animate function. Okay, so pretty much I took prepackaged stuff that somebody else had figured out that I found out on the web, and I just went through and changed it for the function we have. When you get ready to draw one of these, you will take my code and change it for your function. All right. But we have to go ahead and run it. So we get the animation. Boom, 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 boom. And all right. So if you notice the picture there, it goes up, but down much slower than it went up. And then if we go ahead and tell it to play, it comes down there where the peak kind of goes down to the opposite of where it was from that. And it probably looks to y'all like this is doing a reflection, like playing it forward and backwards. But if you pay attention to what's happening with the cursor down here, this is just running through a loop because you have a period of 30 here for your t values. So, and if you wanted to instead have it reflect here, this will, yeah, you got that option. But this animation thing is really just a little JavaScript thing that's built in to Colab. So, all right. So, with regard to the homework stuff, I would like for you all to go look at the animation, and for your coefficients, go back in, put them into this, and get the animation and make sure it actually looks like the initial condition that you started out with at the start. No offense, but some of y'all had pictures that you gave me where the Fourier series that you got looked nothing like the initial condition, and it should. So if it doesn't, then you should debug your code. So I might be talking to somebody who knows about debugging code. You should fix that. So if you're having a rough time debugging it and figuring out what's going wrong, that's what office hours are for. Okay. All right. In any case, though, yeah, use the animate so that you can see kind of how this develops out, and then for the assignment, I would ask y'all to put some pictures in there. Okay. I mean, hypothetically, if you're working things out with a pencil, you can just put pencil to paper and give me a few sketches and give me some guesses about what the t values are that those are happening at. If, on the other hand, you want to be a little bit cooler, you could go in and just figure out how to draw the pictures. Basically, you can do some cutting and pasting to get that to work. Okay, but draw the pictures without animating, and then you can copy and paste into something that allows you to do a little bit of PDF editing. So, all right. So in any case, that is an example, and I will link to things in the video stuff. Let me know what kind of questions that you might have. I'll see you all in class. All right.